Imagine you are running a high-tech manufacturing plant. Your assembly line is producing multiple different tech components, and every item has a different profit margin. Naturally, your goal is to maximize your total profit, but you can't just run the machines infinitely. Your output is throttled by hard physical realities. You have capped labor hours, limited machine runtimes, and finite raw materials. If your factory only manufactured 2 products, finding the most profitable production mix is straightforward. We can solve it visually using the graphical method. This animated diagram plots those 2 product constraints on a simple graph. The intersecting lines create a shaded region of feasible production options. The highest upper right corner of that shape represents the maximum profit you can earn without running out of materials. The problem is, modern factories don't just make 2 items. The moment a business introduces 3, 10, or 100 different products into the mix, drawing a map is impossible, and guessing the correct production volume costs millions in lost revenue. As we see in this animation, adding just one more variable extrudes that flat 2D polygon into a 3D shape. Add a few more, and the geometry fractures into an expanding multi-dimensional lattice of data. Human brains cannot visualize a 12-dimensional object to find its highest corner, but a computer can navigate its structure mathematically. This is the core function of the Simplex method. It systematically feels its way along the invisible, multi-dimensional corners of this data until it reaches the point where no more profit can be extracted from the current constraints. By translating physical constraints into rigid mathematical rules, the Simplex method calculates the specific production mix that yields the maximum possible profit. Before the algorithm can solve the problem, it needs to factory data translated into a strict format called standard form. We start by defining our objective function. This is the single overarching goal we are trying to maximize, in our case, total profit. Watch how this equation changes. Our real-world constraints, like using less than 12 hours of labor, are written as inequalities. The algorithm cannot process a less than statement, so it must be converted into an exact equality. To balance the equation, we introduce a new term called a slack variable. Mathematically, this represents the factory's unused resources or idle time. By standardizing the equations and tracking the unused slack, we lock chaotic physical limitations into a rigid syntax the algorithm can execute. This matrix is the Simplex tableau. We feed our equations directly into this engine to begin the calculation. The algorithm starts at a baseline scenario, producing entirely slack. Looking at the basic variables S1 and S2, the factory is currently building 0 actual products. Therefore, our total initial profit in the solution column sits at a flat 0. Now that the baseline is set, the tableau's primary function is clear. Hunt through the data for an upgrade driving that profit number up. To find the fastest way to make money, we check the net evaluation row at the bottom of the block. The engine locates the highest positive number, 16. This is the entering variable, the product increasing profit the fastest. To see which raw material runs out first, we perform a ratio test on the far right. The smallest resulting ratio, 6, becomes our leaving variable. This pinpoints the exact physical resource that bottlenecks our production. To clear this bottleneck, the engine executes a pivot operation. Using elementary row operations, it transforms the entire mathematical matrix to swap these variables. The new product enters the basis while the exhausted resource is removed. This recalculates every value to show exactly how much resource capacity remains. This creates a continuous loop. The algorithm checks the bottom row for the next most profitable product, performs another ratio test, and pivots again. It repeats this cycle until no further upgrades exist. When the net evaluation row hits 0 or negative at the bottom of the tableau, we reach the optimal point. In the solution column, the factory must produce 8 units of product 1 and 2 units of product 2, yielding an optimized profit of 128. The algorithm has systematically tested every corner of the feasible region, proving that no other combination of these specific resources can yield a higher result. Today, this exact mathematical matrix logic is used to manage massive global operations containing thousands of overlapping variables. Airlines run simplex arrays to minimize jet fuel consumption by perfectly scheduling flight crews. Shipping giants use it to route millions of packages through the fastest possible distribution channels. and algorithms deploy it to balance highly complex financial portfolios. When faced with the millions of potential combinations in a global supply chain, the Simplex method evaluates the constraints and identifies the specific final configuration that maximizes output while respecting every operational limit.